Board of FIA, so they are doing projects together, as for instance Willy Muller, that he will be here in a while. For the ones that they don't know, I would like to say some things about Mike. He's a professor for civil engineering, chairing the Department of Conceptual and Structural Design at Technische Universität in Berlin. And he's the managing director of Schleich Bergermann und Partner, consulting structural engineers in Germany. Mike Schleich worked in Spain, as I was saying before, as a structural engineer before joining Schleich Bergermann and Partner in Stuttgart, which specializes in lightweight and long-span structures. His research at TU Berlin concentrates upon active and movable lightweight structures that can adapt to changing boundary conditions. That would be interesting to see. An intelligent bridge with damping by artificial muscles or experimental structure that fold away when not needed was built at the TU Berlin lab. Mike Schleich received the German Bridge Design Award, Deutscher Brückenbaupreis, in 2010 for the footbridge Sassnitz. So as you see, we also ourselves have a very active lab here. So I would be really glad to host one of your structures. We are always open. So help me welcome Mike Schleich.
Can you hear me well? Is the sound good enough? No? Can you hear me now? All right. Thank you very much for this technical assistance. Thank you very much for inviting me. Yes, it is 5 years ago. 5 years ago I talked about education in structural engineering and civil engineering. Well, there were some people listening at least. I'm a structural engineer, so I'll keep talking about structural engineering, but a slightly different subject today. In a way, it's a history lesson. It's about conceptual design of lightweight structures, and there's a contradiction in this title because conceptual design and lightweight structures is two completely different issues. Because conceptual design means talking about concepts, talking about conceiving a structure, talking about the first design steps that define a structure, and what we want when we define a structure, when we conceive a structure, is quality. We want good buildings. And good buildings not necessarily are always lightweight structures. Now, sometimes we want to have a concert hall which needs a very heavy roof for acoustic reasons. Sometimes we build a dam which has to be very heavy in order to be stable. So what we want is quality. And good quality design, I think, comes from the boundary conditions, from considering the local context. If you study the local context, if you study the boundary conditions, you find out about the topography, about physical conditions, about wind loads, or whatever we have to put as an engineer, actually. If we think about the technological aspects, who can build here, what materials are available. If we think about economy, look at Spain. Today you build different than you built 5 years ago. All these are local boundary conditions that define the quality of a structure, and the outcome can be lightweight structures, but not necessarily. So lightweight structures are not an inherent concept of conceptual design, really. However, lightweight structures are often the result of the concept phase. Lightweight structures are often the result of a design process because lightweight structures do have some qualities. They're light, and we associate lightness with elegance. They're transparent, we can see the flow of forces. We like what we understand, so if we understand the flow of forces, we like these structures. They have a social component because they're difficult to build, so we need qualified engineers, we need qualified builders. And today, that's very important. We can also say lightweight structures are sustainable. They're sustainable because they're really, in the true sense, sustainable because they minimize the use of material. Lightweight structures minimize the expense, so to say, and that is, I think, very special and very modern about lightweight structures. I can speak louder, and perhaps you hear me still. Can you hear me still? Yeah, that's very good still. All right. I'll start with a little table of contents, because it's a very complex thing I'll try to talk about today. First of all, I want to define what is lightweight. What is a lightweight structure, at least from the engineer's point of view. And I claim that true, important, interesting lightweight structures are double curved structures. Concrete shells were the first real lightweight, modern lightweight structures. And one of the masters of lightweight structural design was Felix Candela. So I want to center the middle part of the lecture on Felix Candela. He was the master of concrete shells, but he was also ending with concrete shells. And I want to show you what came after concrete shells, how many new possibilities we have today. And therefore we end today and we have a quick look into the future. So a very long, big subject, but I've got so much to tell you, I already restricted myself quite a bit. I'll start with a little house and a little bridge, and I'll end with a little house and a little bridge. The little house, the one-family house, in my opinion, the prototype of the architect's building, and the bridge, the prototype of the engineer's building. We can discuss this. Lightweight, it could be lightweight materials. At the University in Berlin, we developed a very lightweight concrete. We call it infra-lightweight concrete, and we built a house with it. Did you see it during construction? And these walls are built with infra-lightweight concrete, which is so light that it's floating on water. It's lighter than water. It's full of air bubbles, and therefore it's getting some insulating qualities. It's insulating concrete. Actually, it's load-bearing insulation, and we built this house with it. With pure fair-face concrete walls, no addition of insulation. So this is the house during a normal day when the sun is shining. You can close the shutters, so it works nice in the summer. But more importantly, it's a house in Berlin. It also works in the winter. And it works with concrete walls, concrete inside, concrete outside. No plastic, no styrofoam, only insulating concrete, infra-lightweight concrete. This is not my computer. That I would not call really lightweight structure in the engineer's sense. This I would call a lightweight structure, the way I thought about today. This is the most simple engineering structure, the stress-driven bridge, the Bandadesa. That's a rope that you throw across the river and that you walk on. And these Bandadesas, these lightweight structures, can be converted into modern engineering structures. Here you see that the rope that was thrown across the river has been converted into a steel band, a high-strength steel band that then can carry a very light platform, a very light pavement, so to say. And this I would call a very lightweight structure that uses very little material, that works in a very efficient way of intention only. All this is about engineering here, the house is about architecture, but let's not fool ourselves. We always work in a team. We should always work in a team. Building, modern building is teamwork. And I quickly show you this teamwork structure that was the result of engineers working together with an artist. That bridge is on the invitation of today's invitation. That's why I quickly show it. That was a sketch we once got from an artist. He called us, we worked together, and we had to convert this into a bridge, and this is the result. Again, a stress-driven bridge, but a piece of art. You know, Slinky goes to fame. It's called the Slinky spiral that we perhaps know as children, and the ones that jump down the stairs. So, lightweight structure, result of teamwork, artists and engineers. 2 examples. But let me really try to be precise and define what I think is lightweight structures. And we can follow some principles. If we follow these principles, we'll reach truly lightweight structures, or vice versa. If you look at structures and we find some of these characteristics, we can say they are lightweight structures. We can achieve lightweight structures. You can see here. Can you see my little red dot laser? Very little red dot. Let's try this way. Now you see the mouse now. So one characteristic would be small spans. When we have small spans, we can have little height, little material use. Another issue, another principle is the small relation gamma to beta. That means high strength materials that have low weight. High strength material with low weight, they allow us to build lightweight structures, and the most lightweight and the strongest material these days, I would say, is carbon fiber bands. So I'll come back to that also. If you want to build lightweight, we should avoid bending. We can work with pretension. This mouse is disappearing also. Here's the pretension. And finally, the best trick to reach lightweight appearance, to obtain lightweight structures, is double curvature. To work with double curvature structures, and this is what we'll see a lot today. Where can we find lightweight structures? In order not to get lost, I'll show you this little order of structures. Now try to see my little red dot, it's now in the middle. Here there's like 3 basic structures. On top in compression, you see the arch that works in pure compression only. That's a very simple element. The band below it here, the band that works in tension only, the hanging cable. We have seen the stress ribbon bridge, that's a very simple element. And naturally in the middle here you see the beam in bending. From these 3 base elements, I think we can derive most of the structures we know. And if we go to the first circle, you see, if you go to the first circle here, you see we can derive bridges from these simple elements. At the bottom you see the cable supported bridges, the suspension bridge. At the top you see the arch bridge that corresponds to the arch. And on the left you see the beam bending, the beam bridge. And if you go further out, by translating bridges, you reach the roof area, and by rotating them, you get double curvature and the very efficient lightweight structures that I'll come to in a moment. But let me start with bridges. We started already with the hanging band, and we know this is very light. We reach very lightweight structures because the hanging band works in tension only, and that's very efficient. The entire section is used at the same tension. It's very stable and can become very light. In bending, trouble starts. Bending here on the left side if you use such a bridge. If your spans are small, remember one principle is small spans. Even small spans even stone bridges can be slender, can be lightweight if the spans are light, if the spans are small. You can see this here. Problem starts when you increase the size. Galilei has shown this already. The bone of a pollo, of a bird, is very delicate, very lightweight. But if you increase it, if you go towards the elephant, if you increase the size of your structure, the forces go by the square, the load goes by the cube of the sizing, and therefore the dimensions become very heavy. So a small span bridge can work in bending and be lightweight, but if you increase the size, it will become very heavy. And one trick to still achieve a certain lightness is to shape the bridge. Here is a frame bridge, and you see in the middle, the spans are very, the height. Couldn't I get a laser somehow, a powerful laser pointer, because this is hopeless. And here, in the middle, you can see the forces are high, so there's a large deck here in the corner, and the edges, the bending moment goes towards 0, and therefore also the height is adjusted. Or here in a steel bridge, the shape of this bridge follows the distribution of the bending moments. Where we have high bending, we use high sections, and therefore we can still achieve some lightness by following the flow of forces. Or if you look at this one, the bridge in the front here, this is a composite section that also helps if you use the materials where they work best. at the support here, you have a negative moment, you get tension at the top, steel works good in tension, and at the bottom we have compression. So here we place the concrete. So if you work with composite sections, that helps us also to play with the nuisance of bending to make our structures comparatively light, even though they work in bending. The next step to make our structures lighter is to make them work like a truss, to convert the bending in tension and compression, and then we end up with bridges like that. That's a so-called extra dose bridge that we supervised in India. And you can nicely see that where you have tension, you get the cables, and where you have compression, you get the concrete deck. And here you can go further and further. That is a bridge that was designed by Jörg Schleich and Rudi Berlemann, the founders of our office, and they're still very proud of this first major cable stay which they designed in India. This is a real truss system. You can see how slender these bridges become because they do not work in bending anymore. They work like trusses, cables in tension, the deck and the pylon in compression. And at the time, this was a world record bridge, and not only that, it was indigenous building. And this is why our two seniors are so proud of it, that they could build and design a world record bridge in India, where at the time no one could weld, there was no weldable steel around, there was no high-strength bolts around, but there was a lot of knowledge about riveting, rovlones. You can see here the charcoal drill, and you see here the rivets that they were heating, and they're putting the entire bridge together with rivets. So that is in a way indigenous building and lightweight structures. This one here cost me 5 years of my life. That was a bridge that I was allowed to work on, the Tin Cow Bridge in Hong Kong, and again shows you how slender bridges can become. This is about 500 meters span, and the deck height is 1.70 meters. And that you can achieve by transforming bending into a truss system, by transforming bending into tension and compression. It's the cables that held the deck, and if you would build that as a beam, a concrete beam, probably would be as high as this yellow point here. It would be hundreds of meters high. It would be impossible because bending explodes with the span. What you see here at the bottom is a lightweight cantilever. This is how you build these bridges. You build them step by free cantilevering. And that was a very special moment. This is why I show it, because this was when we were almost reaching the next step. And that was like a 200-meter tower and 300 meters of deck hanging on this tower, slowly moving in the wind and making us all very nervous. You can play. This is very simple systems, and these trusses now you can mold into steel plates. You can mold them into steel sails. And this idea of the extra dose and the cable stay bridge that we have just seen can be converted in such a sail bridge. The structural behavior is exactly the same. The steel works in tension, like cables, and at the bottom where you have compression due to the inclined cables, you use concrete. And this system we have developed for many competitions already. There's just another example here, but unfortunately it's not built yet. So if you're faster than me, perhaps you can do the first still. So there were some examples of working on this first circle of structures, showing you how lightness can be achieved by avoiding bending, by no bending and by small spans if you have to work with bending. So that was the circle here, the first circle of structures. But as I said, real true lightness we can achieve if we work with double curvature. And perhaps you say, well, double curvature, yes, but there was other lightweight buildings, and I accept that. Yes, there was Paxton, there was Eiffel, and they built very lightweight structures when steel came up. In the mid-19th century, real good steel, really high-strength steel came up, and this is when Eiffel and Paxton took the opportunity and started to build lightweight, prefabricated steel elements. But that I would call trusses in a way still. I think a real revolution came when concrete came up, when structural concrete came into the business, and that was about 100 years ago, 110 years ago. this new material became affordable all of a sudden, and it changed everything because it was moldable. It could be formed in any shape, and reinforced concrete allowed to build such structures. That's the shape, that's the reinforcement for a planetarium that was built in 1922 already by the Germans. It was Dischinger, the German structural engineer Dischinger. Thank you very much. Well, I don't need it right now. Anyway, they found at that time new lenses were developed that could be used to light up planetariums, to have projections on circular, spherical faces in order to show the sky at night, to show the stars. The idea of planetariums was invented, and at the same time these engineers found out that they could build such shapes with concrete. So in the 1920s and 30s, lots of shells were built by a team by Dischinger and Finsterwalder. Finsterwalder was the optic expert, and Dischinger was the concrete expert. And they built shells like that. That is from 1932. Make a 10, 12 meter shell with only 1.5 centimeter thickness. And that you can only achieve by double curvature. It's the same idea of the egg shell, right? It can be very thin because of its double curvature. If you would build a beam, a bending beam, it would be 10, 20, it would be 60, 80 centimeters of concrete, but if it's a double curved shell, 1.5 centimeters. Here, in a way, the Germans stopped. The Germans built only what they could calculate. And Dischinger was very good in developing his theories, and he was very good in building these shells. And then others took over in a way. This is a shell by Maillard, the famous bridge builder, Robert Maillard from Switzerland, a shell inserted in the 30s. But the most important shells in the 30s came from Spain. And it was mainly Eduardo Torroja, which for me is one of the most interesting engineers at all. And he developed some beautiful, elegant, lightweight concrete shell. Here's the market in Algeciras, a double curved shell that is supported on 8 corners. And these 8 corners are then connected with a tension band and the 3 edges that are very unstable with thin shells. You see, like on a hat, he folded the edges up and gave them additional stiffness. It's a real little beauty, and if you ever come to Algeciras, don't miss this beauty. It's still there. This one is not there anymore. It's the Fronton Recoletos in Madrid that got destroyed in the Civil War. Another very special structure, very lightweight, cylindrical shells, but not only that. Torroja also showed that the shell can be, discretized into finite elements, so to say. It could be developed into triangles. If you have a triangular shell, that also works like a continuous concrete shell. He knew all this already. He was a real, true genius, and contrary to the Germans who only built what he could calculate, he also built what he could not calculate. And I think that was very, very brave. He built structures like that. That's the Hipódromo in Madrid that you can still visit. It's still there. It survived some bomb impacts in the Civil War, but it survived. And that was could not be calculated at the time. Today we can calculate everything with computers, but at that time it was not possible to calculate such structures. So Torroja built models. He built one-to-one models, tested them, and when he found out they worked well, then he built them even so they could not be calculated. So it's a different approach. And now we come to Candela. Felix Candela was also from Madrileño, but he fought on the wrong side in the war, so he had to flee the country, and he went to Mexico. And there he founded Cubiertas Alas, a very successful firm. He was a real master builder. He was engineer, architect, and contractor at the same time. So he could do everything. And he was very successful with this firm, Cubiertas Alas. And I think they designed about 1,500 shells, and they built about 800 shells all over Mexico. Beauties. And very, very splendid. And there was this bread and butter projects, these umbrellas that later Foster stole for the Lake Salt roofs. I think these are the first examples of concrete umbrellas. Very interesting, you know, he stands on them like the Dischinger guys stood on their shell. And he worked with the hyperbolic paraboloid. He worked with double curved surfaces that are defined by 4 points, point 1, 2, 3, 4. These 4 edges, these 4 corners, these 4 points that define the surface are not in one plane. One point is higher than the other 3, so to say. And if you connect these 3 points with lines, they form a geometry that we call the hyperbolic paraboloid. And he played with this over and over again. He only worked with that, but he derived a very impressive variety of forms. And he even used it for the foundations, imagine. So this is the foundations. Have you ever seen hyperbolic paraboloid foundations? You wouldn't do this anymore today. He used it for everything. This was really wild. And if you drive through Mexico and look around, you find hundreds of these shells. Still, these umbrellas again, but these umbrellas are slightly inclined, and therefore they form shed roofs, you know, so the northern light can get into these warehouses. These are just warehouses, very simple buildings. The drainage goes through in the center, so the drainage is in the support. You find them all over. This is the Mercado de Coyoacán in Mexico. Same system, also these inclined umbrella hyperbolic paraboloids with the light bands. But naturally these shapes did not really make it famous. It was these special structures, and that was the Pabellón de Rayos Cósmicos. It was like an experimental shell to store equipment to test cosmic rays. So the client wanted a very, very slender shell of only 1 centimeter thickness, and Candela said, no, I cannot do this. I can do double curvature, and then I can make it very slender. So in the end, he did it with, I think, 3 centimeters, and that was still good enough. That was his first really famous double curvature shell, which is also derived from hyperbolic paraboloids. And he built everything with it, you know. Many churches, this is also a series of these shells, you know, that meet very dramatically in the center column where Jesus is hanging. So it's very impressive structures that he made. Subway stations. You drive through Mexico City and all of a sudden you see this very wild hyperbolic paraboloid roof in a very normal subway station. Very impressive. And that is one of his most famous buildings, the Bacardi factory. Cuba, how can you say, in the 60s, Cuba turned communist, and they didn't like Bacardi there anymore, so Bacardi had to leave, and Bacardi had to look for a new factory bases, and they built a new factory in Mexico City. So that was the bottling, how do you say, room, or the bottling area for Bacardi. And Candela got the job. And this is still there today. So you can make a visit there and see these very impressive lightweight shells. Everything he built in the end was 4 centimeters thick. He worked everything with 4 centimeters. So this is 4 centimeter concrete shells, and they're still standing nicely. And after you two, you get all kinds of rubber. Be careful. It's a nice bar there. So here again, an example of the hyperbolic paraboloid, and from this shape you can just cut out different sections and then derive all kinds of shapes. And the second famous building is perhaps this one, the restaurant Los Manantiales in Xochimilco in the south of Mexico City. This is a series of 8 hyperbolic paraboloid sections put together to form the roof of a restaurant. Again, 4 centimeter thickness. And this is how it looks today. See the difference? Some 50 years ago, the water level was pretty high. This is a series of canals in the south of Mexico City. Now the water level has gone down dramatically. You see how low it is now, but the restaurant is still standing there. And on Sundays it's open. There's Sunday lunch, and then the couples that go there for lunch afterwards, they start dancing. And look at this gentleman with his white shoes and his white Sombrero was very impressive. So it's still in use, and all this under concrete shell. And the owner of the restaurant is actually a structural engineer, so if you go there and tell him you're from the building business, he gladly opens the roof and you can walk up on the roof. Very, very. My father, some 40 years ago, built a homage to Felix Candela. That was built in Stuttgart with fiber-reinforced concrete, a very early example of fiber-reinforced concrete with 1.5 centimeter thickness. But that was an experimental structure. Actually, Felix Candela came to Stuttgart at the time. My father was very nervous because it could be that Candela would get angry, but he liked it very much that someone had made this copy, and he also climbed on it and tried out how it worked. So he was not angry. Actually, some 50 years ago, my father had designed a shell already with a 100 meter span. That was one of the largest in Germany. And this is here Playa Azul in Venezuela, also designed by Felix Candela. And if you look at these two, there's a striking resemblance. What I want to say is there's a certain legacy of Candela. The Germans then, who in the 20s built these planetarium structures, took over some ideas of Candela and started building shells again, because there was a second high time of shell building in the 50s and 60s. It was 20s and 30s, and then 50s and 60s, up to the early 70s again, when shells were fashion, so to say. That's the finished shell. Candela never built spans longer than 30 meters. That's a 100 meter span. I think that's one of the largest hyperbolic paraboloids built so far. And also at that time, even in the 60s, you could not really calculate such structures. Even in the 60s, models had to be built. You see the loads here, you see this is a plexiglass shape, where you could see the stresses if you use certain light to illuminate it. So this is how these structures were also proved in a way. That's the structure again, and here you see that what the trouble is. You need a lot of expensive scaffolding and shuttering for these structures. That is a problem. I'll come back to that in a second. East Germany, during the communist times, had another master builder. His name is Ulrich Mütter. And he somehow got knowledge of Candela shells, and he built a lot of hyperbolic paraboloids in East Germany. Some 50 shells are still around. And he used the fact that in East Germany material was expensive but labor was cheap. And that helped to build these shells because they used very little material. Again, he used 5, 6, 7 centimeters of concrete to build the shells. We find them all over Eastern Germany still. This is the very north in the island of Rügen, a very nice pavilion, and this looks familiar to us, doesn't it? It's again one of these umbrella shells that we have seen from Candela. So he has used all these ideas in East Germany to make it a restaurant, or it was a bar and discotheque at the time. And it's presently under restoration, actually. Or here, this is one that is still around and in good shape, because this was where the party people from the Communist Party, I mean, had their resort in the island of Rügen. So it was always well maintained. This is actually a hanging shell. This here is not a load-bearing ring. In this initial design, it was transparent plexiglass, so the entire shell is hanging down from the roof. So Mütter was really a brave engineer who used some of the ideas he had obtained from Felix Candela. Oh, that's another little shell at the beach in Rügen, again made of concrete. So East German, the shell construction. This one is further down south. This is Switzerland. This is a series of ice shells designed by Heinz Isler. Heinz Isler is another one of these important shell builders that exploited the capabilities, the potential of concrete. And he showed this to the students at the ETH in the 80s. I was also there, so I could see these. I could see some of his lectures, and it was very impressive how he described how he derived his shell shapes. You know, in Switzerland, in a cold winter day, he would take a wet cloth out in the garden. He would hang it, and then the next morning, when it was frozen, he would turn it upside down. So he played also with this idea of hanging structures and compression structures. So here you see the hanging shape, and the next morning he could turn them around, and he derived the shape of his shells not by calculation, but by models like this. But you need some cold climate, that's for sure, to do this trick. And this is his structures. He did not work with hyperbolic paraboloids. He worked with deriving shape from hanging structures or by pneumatically inflated structures. So it was a different approach, but also he called Felix Candela a master builder. Switzerland is very expensive, so he had to use a different trick, and what he did is he used a very expensive scaffolding, but then reused it several times, and this way he could save money. So you see how carefully this scaffolding was built once, and then he would use it several times to build his concrete shells. So there was, over say from 1920 to 1975, there was hundreds of shells built all over the world. And this is perhaps that's one of my favorites from Isla. But then in the 60s, 70s, somehow these shells started to disappear. And here you see a rather depressed Felix Candela, who was out of business all of a sudden. He was 60 years old, and no one wanted his shells anymore because they became too expensive. The Mexican president had raised the minimum wage, and all of a sudden these shells which need a lot of scaffolding were just too expensive. So it's not only the scaffolding, it's also the shuttering, to the surface for the concrete. It's the very difficult placement of the reinforcement, and it's the placement of the concrete when it's getting inclined, So the cost of these shells went up. The shell shapes, it was the flower power times of the 60s, then shells, the bubbly shells were fashioned, but in the 70s everything became polygonal again, so they were out of fashion. They were also impractical to a certain extent, and insulation became more and more important. In the 70s there was the oil crisis, all of a sudden everything needed to be insulated, and these thin concrete shells lose their appeal if you place lots of insulation on them. So all of a sudden shells became less attractive. And now someone came who turned everything upside down. That was Frei Otto. Felix Candela knew Frei Otto, and he said, well, that's a very interesting young chap. I think the future belongs to him. What Frei Otto did was basically use these shells of Felix Candela and turn them upside down, build tents, which again are double curved, lightweight surfaces. Only that instead of compression, they use tension for working, and therefore they also need to be pre-tension. If you have a tent, you have to pre-tension it in order to give it stability. Oops. Well, So I think that is the structure that made Frei Otto famous, the German pavilion for the Expo in Montreal in 67 or 68, I'm not sure. That was the first example of double curved cable net structures that work in tension, but you can see the shapes are very similar to the concrete shell shapes that we have seen before, only that they work in tension. So here is some typical layout sketch from the 60s where you can show that all these elements are basically the same for these cable nets, only the edges you have to cut in a pattern, and then you can actually place these cable nets plain on the ground, lift them up, and they take their shape. But that's a different story. The climax was soon reached with the Olympic roof in Munich for the Olympic Games in 1972. This is perhaps, or I'm sure, this is the largest cable net in the world, double curvature, pre-tension, and very lightweight. And here's the team. Here these are the guys from Benisch and Mr. Auer. These are the architects. Benisch was the architect, but influenced very strongly and to a certain extent supported by Frei Otto. Here's Frei Otto. That's my father, still young. This is Fritz Leonhard, who was the official engineer. He was the project manager. And here is Bergermann and another gentleman from the university in Stuttgart. So these were the designers of the Olympic Stadium roof, the cable nets in the 60s. And again, these structures were determined, geometrically determined by experiments. They build models, they use these models for determining the forces, and they use these models to determine the geometry. They use photogrammetric equipment to determine the shape. And in parallel, the first computer started. The first computer calculation started, but basically these roofs, which are very complicated, were then calculated by hand and by experiment. And this is the result. Look how lightweight these structures are. And if you come to Munich, this roof is still standing, and it's a must, I think, for people interested in lightweight structures. It's still very impressive to see it. We can do plain cable nets also. This is an example of a cable net that we designed together with GOP architects in Madrid. This is the Malaga terminal. You see very lightweight cable net structures, hanging cables and glass. See the cables here that support the glass. This is basically the same design idea. Tension, cables, glass always leads to lightweight structures. One structure I should mention, even though it was built only once, is a cooling tower made out of cables, made out of a cable net. The system here is a bit different because here is a triangular net, which is more rigid than the rectangular net that you have seen before from Munich. But this is to show you that you can also build cooling towers, which are usually concrete shells in compression, you know that, also as cable shells in tension. If you have a central mass that you use to pre-tension the entire system. So here you see the full-scale tower that was about 180 meters high, a concrete mass in the center, a large compression ring hanging from cables, and between this compression ring and the foundation on the ground, you would tension a cable net composed of triangles. Remember the Fronton Recoletos with Toroca? He has decomposed his concrete shells into triangles, and here's a cable net decomposed into triangles, but in order to make it work as a cooling tower, naturally you also need some cladding. So the finished structure is not really recognizable as a cable net. But here we see both the concrete shell cooling tower and the cable net cooling tower. These type of shells are still used today quite frequently. But if you look at the history of these cable nets, not so many are built these days, because they also have some drawbacks. First of all, you build structure number one, a primary structure, a cable net with, say, 70 centimeters between the nodes, so that's a very tight structure. And then you need to build a secondary system, a cladding, to make it waterproof. And here for the swimming pool at the Olympic Stadium, actually it's three levels. There's the cable net, there's the plexiglass cover, and below it there's a membrane to keep the heat inside. So I mean, this made these structures very expensive. And as I said, you need tension, like a tent. You have to tension these structures, and how do you do this? By tensioning them into the ground, like you would do with a tent. So here you have to anchor a lot of force into the ground, and also this is quite costly. The next picture shows you one of these foundations. See how big they are? So these cable nets need a lot of weight in the ground, you know? And this is what made these cable nets very expensive, the secondary cladding and the large foundations. Still, this is a possibility. Double curved cable nets are an alternative to the concrete shells. Today, there's very high strength membrane materials. So you don't have to have a cable net with nodes every 70 centimeters. You can have cables every 20 meters, and in between place a membrane. So these membranes, again, are double curved, lightweight, pre-tension, but very efficient because they are structure and cladding at the same time. And another trick to make these membrane structures and cable structures very efficient is to make them work as self-anchored systems like the spokeswheel. Because the spokeswheel, as you all know, consists of a compression ring and highly tensioned radial cables. Only because of the high tension in the cable they work. And this turns out to be a very rigid, a very efficient structure, and naturally you all know that you don't need to anchor your bicycle into the ground in order to make it work. And this way, many roofs have been built that follow the same system, the same way, the same idea. The stressings, the pre-tensioning is in the system itself, like in a spokeswheel. You have an outer compression ring, you have an inner tension ring, you have radial cables, and you don't need any expensive tensioning into the ground. And this is why these structures have become very successful, because you have cables only every 10 meters, you have lots of membrane, and they are self-anchored. That is the roof of the Stuttgart Stadium that was built in 1993, and that's one of the first examples of this type of structure. And ever since then, many of these roofs have been built. Here you see the Durban Stadium that was built for the soccer championship in South Africa with GMP architects. And it's an example of, again, the variations you can introduce, the large variety of possibilities. This is a spokeswheel combined with an arch. Also, this is possible. And there's hundreds of examples. Perhaps next time I'll talk about skating roofs in 5 years. But let me come back to shells. Let me come back to structures in compression. Another disadvantage of the concrete shell is that they're opaque. They're rather dark. You have to have a lot of windows around, and you have to punch holes into the shell, which make it difficult if you want light. So why not go to glass directly? And there is early examples of glass shells already from the 19th century in Great Britain, from the colonial times. But these are very exotic structures, and they have always the trouble that there's a certain concentration at the top where all the structural elements meet, and they don't really work as shells. They only work as shells because the glass works together with the structure, and today this will not be allowed anymore. Today, load-bearing glass is not covered by the codes, unfortunately. But again, engineers can use tricks and play with these tricks to make glass shells. And one trick is to use the kitchen sieve. The kitchen sieve consists of a mesh, of a steel mesh, that it can be put plain on the table. If you cut the sieve where I put my laser here, if you cut it here, then this mesh will go plain on the table, like this, and then you can deform it by hand into the shape you want. And the trick here is that all these elements that form the rectangles here are of the same size, so you can build a shell with all elements equal in a very simple way, like a kitchen sieve, and the result is could be like that. Here you have the advantage that you have no concentration of structural elements towards the top. But remember, if you want to shell with the triangles, Opa showed this, and we have seen it with the cable length. And here, if you look closely, these 4 points are connected by cables, by tension cables, and therefore there is triangles again. You know, if you add cables to this initially very unstable rectangular system, then it actually can work as a shell. The problem here is, unfortunately, these 4 points are not in one plane, so you need curved glass, and that is expensive. And here another trick came up, and here I try to exemplify this with the hyperbolic paraboloid again. This is what Candela did. And this is the hyperbolic paraboloid, 4 points which are not in the same plane, and this shape can be nicely developed, this geometry can be nicely obtained by using plane lines. That's very important if you want to concrete your shell, because the shuttering, the formwork, can be made of plain, straight timber elements. Now, if you want to work with glass, you can obtain the same geometry if you use a parabola here, and along this parabola you move another parabola. So actually, this parabola here is always the same, it just moves along this one. And you obtain exactly the same shape. This would be awful to concrete, to build a shuttering like that, but it's very nice for glass, because these 4 points now, because this is a so-called translational surface, are actually in one plane. So such a surface can be built with plain steel elements and plain glass. And the result can look like that. So all of a sudden it's also possible to build double curved surfaces with a steel grid and covered with glass. And there's many examples like that, and the idea is very simple. You see it again here. This is the director line, and this is the generator line. So you move a generator line along a director line, and the the translation vectors, so to say, are parallel, and therefore all these elements are plane. They're not rectangles, they might be skew, but they're all plane, and therefore we can cover them comparatively economical with plane classes. And with such tricks, such simple geometrical tricks, very nice surfaces can be obtained. This is the Museum of German History in Berlin. As an example, architect is I.M. Pei. And it also looks quite nice, also in the details. Here, this is the house of the hippopotamus of the Berlin Zoo, with a nice glass shell. Also here, you can see that the geometry is derived from moving one parabola along another parabola, and you can obtain such free shapes with all plane classes. Well, this is technology from 10-15 years ago. By now, this has developed much further, but I want to show you some very simple tricks, some very simple ideas, principles, how to obtain lightweight structures through double curved surfaces. Or the main train station in Berlin, again with GMP Architects, follows these principles. This is again a translational surface. This way a very long, really actually not very even roof has been obtained. If you come to Berlin, have a look at the Berlin main station. This is how it looks. In Madrid, that was a design won by Alquimatica. These architects converted the Correos, the post office, into the new Ayuntamiento, the mayor's house. And the result, the glass roof they had envisaged, was so free in shape that it could not be done with the translational surface. And if you cannot do it with the translational surface and plain rectangular glasses, you can always do it with triangles. With triangles you can develop any surface, and this is always the last resort. If the shape is very free, then develop it with triangles, and we already know if we build it on a triangular steel grid, then it can actually work as a shell, and it can be very slender. So you can easily cover 30-40 meters of glass shell with steel elements of only 3-4 centimeter thickness. Here, this is another example of a glass roof that we designed together with Frank Gehry in Berlin, just to show you how free these shapes can be chosen if you work with triangles. This is made all of stainless steel. It was certainly not a very economic shell, but I think the result is quite impressive. Here I could end my talk because I have shown you a bit the history of lightweight structures. I've shown you how, in my opinion, lightweight is defined in the structural sense, that small spans allow lightweight because it allow little height, that we should avoid bending and try to work in tension and compression only with the hanging cable or the arching compression, or we combine the two and work with a truss like the cable-supported bridges, but the most efficient way is to work with double curvature. And I use the concrete shells because I think they are the real root of modern lightweight building. As an example, the Spanish history, Candela, and I'm trying to emphasize that this has developed further. Today we have much more freedom than we used to have some 60, 70 years ago. Today we can still build concrete shells. Actually, we can build them much better than in these days because we can calculate everything. We have all these tools that I saw over there to do the wildest shuttering without any big trouble. And they're becoming fashionable again, I think. So concrete shells are there. We can have glass shells, as you have seen. We can do any shapes we want with glass. Glass has become quite economical. We have the cable nets to do all kinds of double curved surfaces also, and we have all these modern membrane materials that allow us to build tent structures. So today the variety of possibilities, the designer's freedom is much bigger than it used to be once upon a time. Well, I said I'd start with a house and a little bridge, and I want to finish that way. And what I'm also thinking about these days is what comes next. To think about what comes next is very difficult. Next comes by itself, but why not try to think a bit about it and to come back to these very simple structures. I want to show you a very modern stress-ridden bridge that we have built in our lab at Berlin University, which has got to do with sustainability again, this very strange word. And I told you that the most potent material these days is carbon fiber. These bands, this is carbon fiber bands, are 10 times stronger than steel. Their weight is only 20%. And this way we can achieve very lightweight structures and reduce material to a real minimum, and therefore are becoming really sustainable. I think the movie here does not work when we try, but otherwise it doesn't. Well, this gentleman wanted to walk on the bridge for you to show you how it's moving. When he walks over this bridge, that is the stress-ridden bridge, the carbon fiber stress-ridden bridge with 10 centimeters of concrete on top of it just to make it heavy. Still, when he walks, this bridge would go up and down like that. It would move up that much. You know, it's hardly usable. And that's the price that you pay for lightweight structures. Lightweight structures become very lively. And therefore, I think we have to develop new means to reduce these liveliness. And we should not go back and build pyramids. Rather, we should do the same as we do in the automobile industry. You know? Invent new techniques to make our buildings and our cars more stable. What was done here was using artificial muscles. So you see here, these are little tubes that are inserted into the handrails. And the bridge is now fully equipped with sensors, accelerometers. So when you move on the bridge, these sensors send their signals to a processing unit, and this processing unit in real time inflates these tubes with compressed air in real time. And these muscles, here you can see them. This is the uninflated tube, and if you inflate them, they can introduce forces into the structure of up to 600 kilos, which is not so bad in the racing. And the force then that is produced here is forced by lever arm is a bending moment that will introduce it. So if you make the bridge move, the muscles in real time counteract. And this is the result. That would be the accelerations, the movement of the unbent bridge, the bridge without muscles. And this is the movement that you produce when the muscles are installed. So if you ever come to Berlin, come by and we'll show you this bridge, because you can really go like that and the muscles work in real time. You go like this and the muscles go. And we just cannot make this bridge move much anymore. It still moves a bit, but not much. So I think this is one thing, one direction we can go towards in the design of lightweight structures. We should really go towards lightweight building because there's not much resources left. But we have to invent intelligent systems to counteract the trouble we are causing with these lightweight structures. We also stand on our structures, like the Dischingers. You know, so this shows you that this bridge can really hold the entire Institute of Structural Engineering at the Technical University. Now, I told you that I also wanted to quickly talk about a house. This is a chalet in Chandernagh, Switzerland. It looks very original. Look at the corner, you know, these very heavy timber elements that go like that. You know? But if you look closer, if you go away from the corner, you see it's all fake. There's lots of insulation here, and then there's like 2 centimeters of timber. Or here, this used to be in the original houses, this would be heavy stones. If you look closely, this is 20 centimeters of styrofoam and then 2 centimeters of glued on fake stone, you know, to make it look the same. So if we today in the building industry talk about sustainability, it's minimizing material, save our resources, but at the same time we always talk about saving energy. We want to save energy in heating, and therefore we put lots of insulation in our houses. And thus we are spending a lot of energy again, because this is also using a lot of electricity electricity and a lot of petroleum. And it's definitely fake and not really lightweight. And I know that we are all in a crisis right now, especially in Spain. And I know that the price for electricity is going up. And perhaps I'm a bit provocative right now, but perhaps imagine if electricity would basically be free, and not only that, if it was very clean and renewable. If our energy we get, and 15 or even more % of the electricity produced in Spain is coming from renewable energies. If we had lots of clean energy, we would not have to save energy anymore. So we could build such structures again, which are really sustainable because they minimize the use of material, and we would not have to use all this insulation. We could build again windows with only one pane of glass. We could even heat our houses with open windows again, and we could go back to real lightweight structures. So perhaps this comes one day, and in our office at least we are working hard on that. We are designing such solar thermal power plants that are still expensive, I agree, but they produce clean energy, renewable energy, and our largest project is this one, the solar chimney. That's a lightweight structure. It's a concrete shell, 1 kilometer high, only 30 centimeter thickness in average, about 100 meter diameter. And this here is a glass roof, a glass house at Invernadero with about 7 kilometers diameter, 40 million square meters. And the sun heats the air under this glass roof. The hot air moves towards the center where this chimney sucks the air up, so it produces some artificial wind, and it moves the turbine. And this turbine then generates electricity. It's not built yet, but if many of those would be built not in Germany, perhaps not even in Spain, but in Africa, in all the deserts of Libya and Egypt and all these countries that definitely need economic growth, then they could produce lots of very cheap and renewable energy, and then we could build lightweight structures again. Thank you. The question was about this insulating concrete house that I showed in the very beginning. That is a prototype, but the material is not new really. How do you call these inflated clay bottles in Spain? Aglita. So this has been around for 20, 30 years already. What we have done with this material is just that we have made it much lighter and much more insulated. We have lost some of the load-bearing capacity, but with 50 centimeters of concrete, you can actually build a house in Germany and still comply with the energy-saving regulations. So what we have done is develop it further, but it's not on the market really yet. So it's a prototype house, and at the university we are doing research on this type of infra-lightweight concrete. Any more questions?
Should I go on with my second one? Okay. I think that one of the last projects that you saw with the masking braids is one of the, it's like a very inspirative project. And I was thinking, why I see this project that, especially nowadays with the economic crisis and all the resources crisis that let's say facing, I was thinking that how do you think that we could create structures that they are not rigid, such rigid anymore, but they are rather more interactive, on the one hand with the user, on the other hand with the environment, so that we could create this kind of ephemeral structures that they are in balance with the environmental needs, let's say. So if you're thinking that sensualizing structures as the one that we saw in the masters, or what kind of other ways we could implement on our structures that we could create this kind of interaction.
Well, as I said in my talk, that I claim that lightweight structures are the way to go, because this is taking care of resource trouble, this is taking care of all kinds of the problems we are facing. They're very complicated, therefore they create jobs. I think that is a good way. And I'm a structural engineer, so I concentrate on structures. And I think this prototype muscle bridge is an example of the direction we could go to make our structures more intelligent. But I also know that in architecture there's many possibilities, and there's a lot of movement if you look at facades, if you look at glasses that change color. So I think it's a general trend to make our structures more intelligent and in a certain way energy saving. But this is a very general statement. My today's claim was lightweight structure is a very modern way to build, and I tried to show you some ideas of the future, but this is my personal attitude. Yes?
I have a question about I love this lightweight structure. I really love all this lightweight structure, but you still say with concrete or steel or glass, some material we used to see for, and I've been explaining for 100 years. But can we use also some other materials that are maybe more sustainable to produce? I know that the concrete or the metal is quite can be pollute a lot the air or the soil. Can we use this the wood with this sort of lightweight structure, or so the material, I don't know, bamboo, or I don't know which kind of structure we can use with this one? Thinking really about the material inside. Something that maybe is not so homogeneous as concrete or metal, but more heterogeneous and maybe more complex to understand.
And you're saying that concrete has been around for such a long time, and you recommend wood, which has been around forever. I mean, if I look at the history, I think the history of building is the history of materials. And stone and wood have been around forever, for ages, ever since. And I think concrete is a very modern material, and if you use it in a clever way, I think it's a very good material. It's the best material. It's very cheap, it lasts forever, it can be easily recycled, but the cement production is very labor intensive. But I wouldn't blame concrete, I would blame very heavy concrete structures, but if you build concrete shells, I don't think you have to worry. I think steel is also very efficient. It can also be easily recycled. And it's also very modern. Imagine reinforced concrete has been around for 100 years. That's nothing. Modern steel has been around for 150 years. That's nothing compared to all other types of buildings. There is modern materials like carbon fiber and all these plastics, but they're still very expensive, and they are not lasting very long. And now comes timber. Timber sounds very natural, right? And it's what do you call it in English? I don't know. It sucks up the carbon dioxide, right? It stores carbon dioxide. It's a carbon dioxide storage in a way. And I'm sure it can be used, it will be used more frequently now, because that is true. But if you want to build long-span structures, if you want to build heavy-duty structures, and I'm talking about bridges and long-span roofs and so forth, the timber is just not strong enough. we have built a concrete, we have built a timber roof with 65 meters span and 150 meter long length, and we ended up using 20 kilos of steel per square meter in this timber roof, because the connections you need are so complicated. Steel is so difficult to connect that you end up spending a lot of steel in a timber structure. So timber is fine for small structures, but that's my opinion. For long span, high-tech, heavy-duty engineering structures, timber is still not the right choice.
Even flexible structure like grid shell?
Yeah. Frei Otto has also done a very beautiful grid shell. That is possible, yes. But again, if you want to really imagine, you have seen these grid shells, the triangles, all these little bars, you know. If you connect them, how do you connect it in timber? You know, this is the tricky question, because you might end up with a lot of steel again. Frei Otto was very brave, you know, he didn't care much, you know. This shell is still standing, but if you build it according to modern codes, and if you really want to make it last for a long time, be careful with timber.
I found quite surprising that you didn't mention Buckminster Fuller in your course through the history of shells. What is your position on his ideas of three-dimensional shells?
Yeah, this is very good. I need to go back to, I have implicitly mentioned Buckminster Fuller. Because I showed you a geodesic dome. Look, I've got 115 slides already, and if I start talking about Buckminster Fuller and his geodesic domes, this would open another world, right? And I wanted to concentrate on the European shells and double curvatures, but if we talk about Buckminster Fuller, we should say this is the first geodesic dome designed in 1922, and Buckminster Fuller came some 50 years later with exactly the same system, no? With pentagons and hexagons, and he was very successful with that. Actually, his major geodesic dome was just at the same time as the tent of Frei Otto. No? But that would start, and I agree he's also important, and quite a number of other important people around. It's just I could not mention them all. All right, thank you.